Now let us take an example for hydroboration using dicyamyl borane followed by acidolysis. Come on. So this is butadiene, right? Now when butadiene is treated with let us consider dicyamyl borane with a deuterium. Then, of course, acetic acid with the hydrogen. This is when we need the mechanism. Because they have given two different things. If both are deuterium, then there won't be any issue. Even when both are hydrogens, then also there won't be any issue. But when one is deuterium and the other one is hydrogen, which one has to be added to which carbon atom? This is where the interesting part lies. And of course, we know that this deuterium goes to this carbon, and of course, the hydrogen goes to this, right? As per the mechanism. Come on. CH3, then this will be deuterium, then this CH3, then here it is hydrogen. Okay, so that's it. So the deuterium is from the dicyamyl borane and hydrogen is from acetic acid. So these are all syn additions. Let us now go for anti-addition using another interesting reagent. The same hydrogenation. Come on. Alkyne. See, here we can use the regular sodium in liquid ammonia. Or else, in place of sodium, we can also use lithium in liquid ammonia. More frequently used. Now, these are also used. Sodium in ethyl alcohol, even lithium in ethanol. So these of course, are called Birch reduction reagents. These are meant for anti-addition and of course known as Birch reduction. So here we get a trans product. So with Lindlar's we get a cis product, whereas with the sodium in liquid ammonia we get trans product. Okay. Now there is an exception for this. What is that? Supposing if you go for something like this or something like this. See, these are called terminal alkynes. Of course, the second one is acetylene, right? Whenever we go for terminal alkynes with sodium in liquid ammonia, we get the hydrogen replaced by metal. So what do we get? R, C, triple bond, C minus, Na plus half hydrogen. Right. But why? See, when terminal alkynes are treated with sodium in liquid ammonia, you know, these acidic or active hydrogens get replaced by the metal, and you get what is known as sodium alkynide. Okay, sodium alkynide is what we get. In case of acetylene, of course, we get monosodium acetylide, even disodium acetylide when both the hydrogens are replaced. Okay, remember one thing, we call these hydrogens acidic. It is because, you know, the triple bonded carbons are of sp type. They are sp hybridized. See, in a bond with the sp hybridized carbon, the percentage S character is 50, right? It is a known fact that when percentage S character increases, they'll be more closer to the nucleus because S electrons obviously are more closer to the nucleus, right? They'll be much closer. As a result, electrons are more attracted, more bound to the nucleus. So electronegativity will be more. So when electronegativity increases, acidic nature also increases, right? That's it. So hydrogens attached to a triple bonded carbon, nothing but the sp hybridized carbon, are acidic or active hydrogen. This is an interesting. Except when you got terminal alkynes, you get a trans alkene. So this is about hydrogenation. Of course, partial. Now let us go for another preparation method, that is dehydration of alcohol. Okay, a very interesting thing which follows even mechanism. We know that. Let us consider a general alcohol. Now there are many dehydrating agents which remove water molecules. Dehydration, nothing but removal of water. Let me give you the list of things. You can go for the regular concentrated sulfuric acid. And I think you all know that in the preparation of ethylene, we go for concentrated sulfuric acid at 170. You can also go for concentrated phosphoric acid, alumina, even alumina along with pyridine. This is your pyridine. Okay, different sets. Even thorium dioxide, thionyl chloride, SOCl2. Of course, PCl5. See, all these are the different dehydrating agents, which of course are useful for removing water molecule. Of course, I'll give you the mechanism, but for now, this is the product. Now, let me give you the mechanism and information about the different dehydrating agents and their speciality. Okay, in the mechanism, let us take acid catalyzed dehydration. Consider propan-2-ol. In the presence of acid catalyst, see the mechanism carefully. Now we have lone pair set oxygen. See, the lone pair is given to a proton, so we consider it as a base acid reaction. This step is fast. See, we get CH3CH, then O, you already got a hydrogen, still there is a lone pair, now got a H plus. H, the oxygen gets the positive charge because it has just 5 electrons around it, as against 6 what it has to have. Come on. CH. Now, this one loses a water molecule. Then a carbocation is generated. Okay. Now from this, we can get an alkene this way. For convenience, let me take the methyl group in this way. Use a water molecule again. Say this. Water molecule abstracts the hydrogen without the bonded pair. Bond goes to the rescue of the positive charge. That's it. We get CH3, CH, then double bond, CH. Okay. So this is the mechanism of acid catalyzed dehydration. Now, let me give you a very interesting example, which has got everything. Come on. Supposing if a question is given with this alcohol on dehydration with concentrated sulfuric acid. Come on, concentrated sulfuric acid gives a H plus, acid catalyzed, the same mechanism. Okay. then H, you still have a lone pair, and of course a positive charge. Then the same way as in the mechanism, a water molecule is eliminated. You get a positive charge here. See, this is a 2-degree carbocation. See, whenever a carbocation is the intermediate, we know that rearrangements are possible. But see, for example, you want all possible products, then see there are different possibilities here. See, this is a beta hydrogen. Here you got one beta hydrogen. Let this be possibility number 1. Even this also a beta hydrogen. Let us consider a hydrogen out here. Even here also you can take a hydrogen out. Of course, you have 3 hydrogens, but say the first possibility and this is the second possibility. Okay. So before going for any kind of rearrangement, if you consider the products formed, come on. In the first case, when this one comes to the rescue of the positive charge, the product formed will be, look at this carefully. It will be this, right? Okay. Then let me just put it 1. Put 1 here. First possibility. Then coming to the second one, I mean, when this goes to the rescue of the positive charge, then the product formed will be this. Okay. Then, of course, this double bond here. See the difference. These are the two things what we get. We'll see what the major product is later. But see, before going for the rearrangement, we get these two products. Now go for shifting. Okay. Now let us consider 1,2 hydride shift. So that, okay, let me show it using this. See, if you go for this, see what happens. Using different colors only to make you understand properly. Come on. This one is okay. Yes, you get a positive charge here. That's it. Yes. Now we got a 3-degree carbocation, which is of course more stable when compared to 2-degree. Now, again the same thing. Go for different available possibilities. See, this is a beta. This is another beta. This, of course, is another beta. So there are 3 possibilities here. Okay. Now with these three possibilities, let us check what we get. Come on, let this be the first possibility. Okay. A hydrogen needs to be taken out, which can actually go for the rescue of the positive charge. So this is the possibility number one. Or else, to avoid confusion, let us consider this to be 3. What do we get? 6. Now this is okay. This is okay. We get a double bond over here with the possibility number 3. This is what we get. I can tell you very clearly that this is going to be the major product. You can check that this particular alkene is a more substituted one. It's of course sets up product. Point number 1. It has got more number of hyperconjugable hydrogens. Then let us go for the second one. Now take a hydrogen out from this area. Okay, even this can come to the rescue of the positive charge. So let this be possibility number 4. You need to be very careful. What do we get? Come on. This. Yes, a double bond over here. That's it. So this is our possibility number 4. Okay. Then there is another possibility. Take a hydrogen out here. Of course, you got 3 hydrogens there, but this is my 5th possibility. Come on. See, we get this, a double bond over here, then this. Hope this is clear. This is our 5th product. See, we have one more interesting step in this. See, when this one further undergoes 1,2 hydride state, you already got a 3-degree one, but still if suppose you go for 1,2 hydride of this type, same, the red one, what do you get? See, you'll get a triple bond here. Sorry, positive charge here. I mean a tertiary kind of carbocation again. This is what we get. And even here also we got 2 possibilities. Beta, not just 2. Of course, these 2 are of the same type. Even this also a beta. But anyway, we got a product with a double bond here. It's already there. So we are not going to go for this possibility. Leave it. Then the final thing is I can see even these two beta are in the same environment. Take any of these. Let me take a hydrogen from this area. Okay, so this. Either you can take this or another from this area, but both will be of the same type. The final thing will be this. Okay, then this, then this, then this. So this is, of course, the final thing, what I wanted to say. So let this be the sixth possibility. Some may be of the same type, but you be little careful. This area is okay. See that this area is also okay. Now, of course, this is the second variety. Okay, so there are different possibilities. Check this out carefully. But interesting is this, the major product, more substituted or the ZF product. So remember with the concentrated sulfuric acid, we have a rearrangement possible and we get ZF product as the major product. That is important. This is very interesting. Now, see when 1 degree alcohols are considered, the primary alcohols follow E2 mechanism. You all know that. Especially when ethyl alcohol is used. Come on. Okay. Now take acid. Then of course, see as and when a stronger base abstracts the hydrogen, this goes here. Let me actually show you this. As and when this comes, this will just go up. So you'll get ethylene. Okay. Now suppose you got something of this type. Very important for solving the question. See, I've taken something which is electron releasing. On one end and electron withdrawing on the other end. Look at this. So this is electron withdrawing group. If it is given this way, and if this is the question, what will you go for? Where will you generate your positive charge? Will it be on this or on this carbon? Because both are of benzyl type. Benzyl carbocations are what you are going to get. But the point is where to generate a positive charge. Remember, when you generate a positive charge, see that it is assisted by something which is releasing. Okay, so let us generate a positive charge here on this carbon. Then that will become benzyl. Of course, even on the other hand also it is benzyl only. But this benzyl is okay because the positive charge is stabilized due to the electron releasing nature of the methoxy group. Never ever generate a positive charge on this, because if you generate a positive charge on this, you will get destabilized because of the electron withdrawing group. See that the positive charge is generated on that particular carbon, which is assisted by, supported by the electron releasing group. Now, let's see the mechanism. I did not write the OH. This is where I have the OH. Now, see the mechanism. As usual, this. So then, okay, let me show you in one step. As and when the OH group attacks the H plus, of course, it becomes OHH with a positive charge. Then the bond just goes off and you get this positive charge. And this bond comes to the rescue of the positive charge. Okay. It goes for a 1-2 shift first. Let me show you that before going for this. So firstly, you get a positive charge here, but when it goes for 1-2 hydride shift, you get a positive charge here. That is okay. So let us just see what happens. OMe. Then here, in fact, we got a positive charge on this carbon. Okay. This will be, of course, a CH2. Then you already got a CH2 here. Then this NO. But now we need a hydrogen to come to the rescue of the positive charge. So let me take this hydrogen out. And now this will come here and the positive charge is neutralized. So the final product that we are going to get will be this. Okay. And this is OMe, CH, double bond CH, CH2. Okay, so this is going to be the major product. Of course, there are some other possibilities, but going for the major one, this is the major product. This is an interesting example.